everyone. Today we're going to review 5.4. I have on slide 112 that's more trig graphs. In reality, I want to focus on tan. The other trig functions really can follow suit if we model them closely based on the tangent function. I have here that the functions tangent and cotangent both have a period of pi, not 2 pi like sine and cosine. Tan of x plus pi is equal to tan of x. Cotan of x plus pi equals the cotan of x. So we discussed in 5.3 that a period is a cycle or a length of one complete cycle. So for sine and cosine, a full cycle happens within 2 pi radians. We're going to see that this is also the case for secant and cosecant, the reciprocal functions of sine and cosine also have a period of 2 pi. Now, secant and cosecant, although they have a period of 2 pi and a full cycle length happens in 2 pi radians, they're going to have vertical asymptotes just like the graphs of tangent and cotangent. And we're going to see why. But firstly, let's understand that a full cycle or period of tangent and cotangent happens within pi radians. And we had this in 5.3, and in the video of 5.3 I put up the graph of tangent, and I'll do it again here. But before I do that, I have notes on slide 112 on page 56 that say, first thing you should notice on a table of values is that the tan of pi over 2 is an error. If we remember the reciprocal functions, tan of x is equal to the sine of x over the cosine of x. Now, tan x is sine x over cosine x means that wherever cosine of x equals 0, if cosine of x equals 0, tan of x would be undefined because we can't divide by 0. It's a violation of the domain argument that we learned way in the beginning of the course. So the graph of tan will have a vertical asymptote at negative pi over 2, pi over 2, 3 pi over 2, and every interval of pi, that is a multiple of 90 degrees. The graph of cotan has a vertical asymptote. So if I look at the graph of cotangent of x, cotan of x is cosine x over sine of x. That means whenever sine of x equals 0, we'll have a vertical asymptote. And I had listed values on the slide as well. Now if we're looking at secant and cosecant of x respectively, well, since cosecant of x is 1 over sine, so again, whenever sine of x is 0, we're going to have vertical asymptotes. It's the same with cosecant of x. And secant of x, wherever cosine is 0, we're going to have vertical asymptotes on the secant of x graph. So that's why I say secant and cosecant really have a similar style in graphing because they are reciprocal functions. So to graph every single one of them might be a little bit of an overkill. We can do it on our graphing calculators. You have plenty of homework problems that can do it. But I'm going to go over the graph of tangent now, again, because it shows up more frequently than any other graph. And the graphs of reciprocal functions we can always derive based on our knowledge of tangent. So let's take a look at the graph of tan again. That's on slide 113. It's replicated a second time for you. Knowing that the period or full cycle length is pi, we're going to see that the cycle of tan repeats every pi radians. So the standard tan function, if I were to graph it on an axis, at 0 degrees, and again we can make a little side table if we want to say when x is, what is the tan of x going to be? So when x is 0 degrees or 0 radians, the sine over the cosine of 0, sine of 0 over cosine of 0, would give me 0 over 1 or 0. So I have a point here. Now at 45 degrees, if I want to go 45 or pi over 4, that's if you want your axis tick marked in pi over 4. We know that at pi over 4 radians, or 45 degrees, sine of 45 over the cosine of 45 is going to be a 1. At 90 degrees, or pi over 2 radians, the sine of pi over 2 over the cosine of pi over 2, using our unit circle, would be 1 over 0, which does not exist. So here I got a vertical asymptote. At 3 pi over 4, I get a negative 1. And at pi, I get a 0 again. So what I get is sort of a disjoint graph from 0 to pi. That's one full cycle. Now instead of having these two halves represented this way, we typically like to graph a full cycle of tan from negative pi over 2 to pi over 2, or from negative 90 to 90 degrees. That's a total of 180 degrees. And we get the full cycle here. I'll draw it for you in red. So instead of going from 0 to 180 degrees, or from 0 radians to pi radians, we go from negative 90 to 90 degrees, or negative pi over 2 to pi over 2. That gives us a complete cycle of tan. Y equals the tangent of x. And again, why does it look this way? Because at 90 degrees, the sine of 90 is 1 and the cosine of 90 is 0. We have a vertical asymptote here. At negative 90 degrees, or negative pi over 2, if we do the sine of minus pi over 2 over the cosine of minus pi over 2, well, we know that using our even odd properties, the sine of minus pi over 2 is minus the sine of pi over 2, which is minus 1. The cosine of minus pi over 2 is the same as the cosine of pi over 2, which is 0. Negative 1 over 0 is a DNE again. Or you could have graphed it on your unit circle and said, if I go negative 90 degrees, what point am I on? Well, negative 90 degrees is 270 degrees. That point on a unit circle is 0 comma negative 1. So the sine of negative 90 is negative 1, which I have here, and the cosine of negative 90 is 0. Negative 1 divided by 0 does not exist. So I have a vertical asymptote here and a vertical asymptote here and a full cycle of tan in between. Now here, the concept of amplitude and period, just as we did in the sine and cosine functions, amplitude really means max height, and we looked at the value in front of the tan x function. Period, we see here that we have a period of pi. So what is the amplitude here? How can we change the period? Can this be shifted left or right? Yes, it can. But firstly, this is the basic tan function. This is what it looks like. If I were to ask you to graph secant, secant is 1 divided by cosine. Secant of x is 1 divided by the cosine of x. So since secant is 1 divided by cosine, wherever cosine would be 0, or every 180 degrees minus pi over 2, 3 pi over 2, we would have a vertical asymptote. So the graph will look different for secant of x, for cosecant of x, for cotan of x, and I invite you to please use your graphing calculators. It's easy enough. If I want to graph the secant of x, How do we do it? We go into the y equals portion of our graphing calculators, clear out what we had before, and secant is 1 divided by the cosine of x. So 1 divided by the cosine of x, close the parentheses, that should give me the graph of secant. Again, let's make sure that our mode is in radian mode, which it is. If we just hit graph, we're going to be in trouble, so let's hit zoom 7 for zoom trig. And we see a really funky graph. Now I know that the period for secant is 2 pi, so I can go back to window and say from x min of 0 to an x min of 2, x max, sorry, of 2 pi by a scale of, let's say I want to go by pi over 2 radians. And then graph it. Well, let's see what happens. That's negative 90 degrees, and I know that at 90 degrees we have a vertical asymptote, and then at 270 degrees we have another vertical asymptote. So we see we have vertical asymptotes happening, and this gives us a full cycle of secant from 0 to 2 pi. So you guys definitely have the ability to graph y equals secant, y equals cosecant, which is 1 over sine instead of 1 over cosine. Cotangent, which is cosine divided by sine. Also similarly, you can check what the pictures of all these look like in your graphing calculator or in your textbook, right? But more likely than not, I hold my students responsible for the 3 basic graphs, sine, cosine, and tangent, with the full knowledge and understanding that the graph of tangent having a denominator that can be equal to 0, just like when we went over our rational functions, will help set you up to graph the other reciprocal functions. Now the next slide, 114, we'll have transformations of tan and should also have cotan, tan, secant, and cosecant. So the first line, y equals a tan kx, and a, that should say cotan kx. So y equals a tan kx and a cotan kx. Just like we had beforehand. A tan kx and a cotan kx. So here we still have a concept of amplitude because there is a variable in front of tan or cotan, but graphically we can't say that it represents the maximum value that the graph will attain, because if you remember the graph of tangent that was just up, the vertical asymptote here means at pi over 2 radians that y's are going to positive infinity. So there's no real maximum value for y. So the concept of amplitude as being a max value sort of is shattered with these reciprocal functions because of the vertical asymptotes. But period still holds true. The period, standard period is pi, but when I have a multiple or a constant in front of x, the period becomes pi over k. Just like in 5.3, when we went over sine and cosine and changes to the period as 2 pi over k, for tan and cotan, changes to period in terms of putting a constant in front of the x variable would make the cycle length shorter or longer, depending on the value of k. If k was a half, I'd be stretching it out. If k was a quarter, I'd be stretching it out. If k was a 4, I'd be squeezing the two sides together and making the cycle length shorter. For cosecant and secant, the period would be 2 pi over k. Because again, a full cycle length is 2 pi. By putting a k in front of the x, I can now affect or change the length of that period. Now I have an example, y equals 2 tan x minus pi over 4. Here, I can't really say what the amplitude of the graph is. You can say 2 or absolute value of 2. Period is going to be just pi divided by k. K is a 1. There's a 1 in front of the x. This does have a phase shift. So here we're having the k parentheses x minus b, just like we had in 5.3. The phase shift here, we're going to be shifting tangent pi over 4 units to the right. So if I took a standard tan graph like this one and then doubled or put a 2 in front of the tan, what that would do is stretch the points on the graph out to make the values more extreme, like the red graph now. That would be y equals 2 tan x. Again, no real concept of amplitude, because in the red graph and in the black graph, the y values go up to positive infinity and down to negative infinity. Between y equals tan x and 2 tan x. But the difference here is with the phase shift. So now if I move this whole graph pi over 4 units to the right, I'm moving it with the vertical asymptotes. Before, if I had a full cycle from negative pi over 2 to pi over 2, and I move it a quarter of a pi over, well, negative 1/2 pi plus a quarter becomes negative 1/4 pi, or negative pi over 4. Positive 1/2 pi plus a quarter is 3/4 of a pi. Is where the other vertical asymptote is going to be. My 0 was at 0, 0, that's moving to pi over 4, 0. And then I have the double effect. The 2 tan x minus pi over 4 shifts it to the right. Bad place to put it. So that would be a phase shifted version of the graph. Now changing the period, if this had a 2 in front of it, for instance, that would mean that the 2 here would mean that now the period is not pi, but pi divided by 2. So I wouldn't have a range of pi radians, but pi over 2 radians. That would have meant that here I squeezed the graph together. I would have gone from negative pi over 4 to pi over 4. So again, it's very similar to what we did in 5.3. Changing the period will change the cycle length. Changing the phase shift will push out or push over to the left or to the right our graph. Changing the amplitude will have the ability to stretch the graph out. And in order to do all of these, you really have to have a solid foundation or knowledge of the basic graphs. And all 3 basic graphs are in your slides. If you have any questions, please feel free to reach out. You know how to reach me, guys. Good luck.